Category O, Lecture 6, Characters. So let's start with recalling what characters of weight modules are. So let G be a semi-simple finite-dimensional complex Lie algebra with a fixed triangular decomposition G is equal to n minus plus h plus n plus, where h is the Cartan subalgebra, n plus is the subalgebra corresponding to our choice of positive roots, and n minus is the subalgebra corresponding to the negative roots. Recall that a G module M is called a weight module if it decomposes into a direct sum of weight subspaces M lambda, where lambda is a weight, that is an element in the dual space of the Cartan, and M lambda consists of all elements M in M, on which elements from the Cartan act via scalars prescribed by lambda. So now we can define what a character of a weight module is. The character of a weight module M is a function with domain H star and range the set of all non-negative integers and infinity. And this function, usually denoted by CHM, assigns to a weight lambda the dimension of the weight space M lambda in the module M. And let us note that the notion of character refines the notion of the support, and the notion of the support coincides with the support of the character function. This is the set of all lambdas for which the character M of lambda is non-zero. Let's observe that simple highest weight modules are uniquely determined by their characters. In fact, they are already uniquely determined by their support, of course up to isomorphism. So let's now discuss the algebraic structure which is formed by all characters. For a weight lambda, we denote by exponent of lambda the function from h star to non-negative integers, which assigns to a weight mu the value 1 if mu is equal to lambda, and to all other mu it assigns the value 0. And for a function kappa from h star to z, we define the support of kappa as the set of all lambdas on which the value of kappa is non-zero. Consider now the set x of all functions from h star to z, such that support of this function belongs to a finite union of the sets of the form lambda plus a linear combination of negative roots with non-negative integer coefficients. Recall that this set, lambda plus the set of all linear combinations of negative roots with non-negative integral coefficients, coincides with the support of the Verma module delta lambda. From this, it is very easy to see that for any module in O, the character of this module belongs to the set X. And of course, it is trivial from the definition that each function, the exponent of lambda, belongs to the set X. So this function has support consisting of one point lambda. So for two elements kappa 1 and kappa 2 in X, we define their sum pointwise. The value of kappa 1 plus kappa 2 at the weight mu is just the sum of the value of kappa 1 at mu plus the value of kappa 2 at mu. And it is very easy that this makes X into an abelian group. Directly from the definition, it follows that we can write every element kappa in X in the following form. So kappa is equal to the sum, this might be an infinite sum, the sum over all lambda in the support of kappa, the value of kappa at lambda times the exponent of lambda. So now let's go further and define on X the structure of a ring. We define the product of the exponent of lambda and the exponent of mu to be the exponent of lambda plus mu. Note that given two functions kappa 1 and kappa 2 in X, and any fixed lambda in H star, there are only finitely many pairs of weights, mu and nu, from the support of kappa 1 times the support of kappa 2, such that lambda is equal to the sum of mu and nu. And this is true because of our restrictions on the supports of kappa 1 and kappa 2. Consequently, using biadditivity, we can extend the previously defined multiplication of the exponent functions to a multiplication on the whole set x, which makes x into a ring. And the zero element of this ring is the zero function. It assigns to any weight the value 0. And the identity element is the function, the exponent of 0. So it assigns to the 0 weight the value 1, and it assigns to all other weights the value 0. One can note that the 0 element of x is the character of the 0 G module, and the identity element of x is the character of the trivial G module. Let us now discuss connection between the ring structure on X with certain construction on modules. Our first observation is that for any pair of modules in category O, the character of the direct sum of these modules is equal to the sum of the characters of the individual summands. This follows directly from the definitions. A more interesting observation is that for any pair of modules in O, the character of the tensor product of these modules is equal to the product of the characters of the individual factors. This observation follows from the fact that given a vector v in m lambda and a vector w in n mu, so v has weight lambda and w has weight mu, the tensor product of these two vectors, v tensor w, is again a weight vector of weight lambda plus mu. Directly from the definition of the product, we deduce that the ring X is commutative. And this can be compared with the property that the tensor product of G modules is commutative. The tensor product of M and N is isomorphic to the tensor product of N and M. One could also observe that for two modules M and N, the tensor product of these modules doesn't belong to the category O in general. So let us now pay closer attention to characters of Verma modules. For a non-zero weight alpha, let us denote by 1 divided by 1 minus the exponent of alpha, the function 1 plus the exponent of alpha plus the exponent of 2 alpha plus and so on. And if we choose alpha to be a linear combination of negative roots with non-negative integer coefficients, then the function 1 divided by 1 minus the exponent of alpha belongs to x. So now we claim that for a weight lambda, the character of the Verma module delta lambda is equal to the exponent of lambda divided by the product over all negative roots alpha 1 minus the exponent of alpha. In order to prove this, we recall that the Verma module delta of lambda is isomorphic to un minus as un minus module. So therefore, the character of delta lambda is equal to the exponent of lambda times the character of un minus when considered as the adjoint module over the Cartan subalgebra. By the Poincaré-Birkhoff-Witt theorem, un minus can be written as the tensor product of the universal enveloping algebras of each individual negative root. And since the character of the universal enveloping algebra of the individual negative root alpha is equal to 1 divided by 1 minus the exponent of alpha, we get our claim. So let us now discuss a little bit the notion of the Grothendieck group. Given an essentially small abelian category, the Grothendieck group of this abelian category is the quotient of the free abelian group generated by the isomorphism classes of objects in this category A. So since A is essentially small, the isomorphism classes of objects form a set. So we take the free abelian group generated by such isomorphism classes and factor out all relations of the form the class of Y is equal to the class of X plus the class of Z for any short exact sequence X is a submodule of Y and Z is the corresponding quotient. For example, if our category A is the category of finite dimensional modules over some finite dimensional associative algebra A, then the Grothendieck group of this module category is isomorphic to the free abelian group with bases given by the classes of simple A modules. Furthermore, in this example, for any A module M, the class of M in the Grothendieck group of A mod is equal to the linear combination of simple modules with coefficients given by the composition multiplicities of these simples in our module M. It is very easy to see that the Grothendieck group of the direct sum of two categories is isomorphic to the direct sum of the Grothendieck groups of the individual summates. So now let us discuss the Grothendieck group of category O. So from the previous example, it follows that the Grothendieck group of category O is the free abelian group with the basis given by the classes of simple highest weight modules L lambda, where lambda is a weight. We claim that the Grothendieck group of O has another basis which is given by the classes of Verma modules. To explain this, we note that by construction of Verma modules, the composition multiplicity matrix of Verma modules over simple modules, that is the matrix whose coefficients are the composition multiplicities of simples L mu in Verma modules delta lambda, is a non-strictly upper or lower triangular matrix, it depends on how we choose our ordering, with ones on the diagonal. So in particular, this matrix is invertible, and hence the classes of Verma modules also form a basis in the Grothendieck group of category O. We also know that because of our direct sum decomposition, we can consider this claim for each of the indecomposable blocks of O separately, or for each of the central character blocks of category O separately. Our next observation that even the classes of indecomposable projectives in category O form a basis of the Grothendieck group. To prove this, we recall the BGG reciprocity, which tells us that the multiplicity matrix of projectives over Verma modules, which mean the matrix which compute the multiplicities of Verma modules as subquotients of the Verma filtrations of indecomposable projective modules, this matrix is the transpose of the multiplicity matrix of Verma modules over simple modules. In particular, it is also a triangular matrix, now lower or upper depending on the choice of the previous of the ordering. It will be the opposite case from the previous one, and also has ones on the diagonal. So this matrix is invertible, and hence it follows that the classes of projective modules also form a basis in the Grothendieck group of O. So now how is the notion of the Grothendieck group connected to that of characters? We claim that for a module M in O, the mapping from the Grothendieck group of O to our additive group X, which maps the class of M to the character of M, is an injective homomorphism of abelian groups. So this follows directly from the fact that characters are additive on short exact sequences. In other words, given a short exact sequence, M is a submodule of N and K is a corresponding quotient, we have that the character of N is equal to the character of M plus the character of K. So this is okay for modules in category O because they are all weight modules. So if we take this fact and combine it with the fact that the characters of simple highest weight modules in O are linearly independent, because simple highest weight modules are uniquely determined by their supports, and in particular by their highest weights, and the exponent functions which correspond to highest weight of different highest weight modules are by definition linearly independent. So this observation motivates the following interesting problem: how to determine the characters of simple highest weight modules in category O. So we will discuss parts of this problem today, but the final answer will be discussed later on during the course. So today we will discuss a special case of the answer, and this is the answer for simple highest weight modules corresponding to integral, dominant, and regular weights. And we know that this is exactly the case when the corresponding simple highest weight module is finite dimensional. Recall that we have previously defined the special weight rho, which is given by the 1/2 of the sum of all positive roots. And for an element W in our Weyl group W of G, we define the sign of W as usual. This is -1 to the power the length of W. So the character of the simple finite dimensional module L lambda is given by the following formula, which is usually called Weyl character formula. So the character of L lambda is the following fraction, where in the numerator we have the sum over all elements in the Weyl group, the sign of this element times the exponent of W applied to lambda plus rho. And in the denominator, we have a similar sum over all elements in the Weyl group, the sign of the element times the exponent of W applied to rho. So let's first discuss the denominator of this formula. So the sum over all elements in the Weyl group, the sign of the element times the exponent of W applied to rho. So we claim that this denominator of the Weyl character formula is equal to the following element, we denote it by D for denominator. So the product of the exponent of rho times the sum over all negative roots, 1 minus the exponent of alpha. And this element we should remember from our character formula for Verma modules. Proof. For any simple root alpha, we have that the left-hand side of this formula changes the sign if we apply the simple reflection S alpha. So this is clear because of this sign coefficient in the sum. Recall that for a simple root alpha, we know that the corresponding simple reflection S alpha swaps alpha and minus alpha and permutes all other positive and all other negative roots. So it permutes all other positive roots and it also permutes all other negative roots. Hence, for a simple reflection alpha, if we apply the reflection S alpha to the right-hand side, we note the following, that S alpha will send rho to rho plus alpha, so this is one of the computations we did before. Then the factor 1 minus e to the power alpha will be mapped to 1 minus e to the power minus alpha. This is because S alpha swaps alpha and minus alpha. And the product of all the remaining factors remains the same, because all other negative roots will be just permuted. And now it is easy to see that what we get is equal to minus the right-hand side, because if we now multiply in e to the power alpha into this factor, we get the change of the sign. So application of S alpha changes the sign on the left-hand side, and it also changes the sign on the right-hand side. Since all exponent functions are linearly independent, in order to prove the statement of the lemma, we need to check that the coefficient at one of these factors on both sides is 1. So let's compare the coefficient at e to the power rho. So this is obviously 1 on the right-hand side, and it is directly from the definition 1 on the left-hand side. And of course, all exponents of lambda on the right-hand side, which do not belong to the W orbit of rho, they cancel if we open all brackets and multiply them in. So it follows that the left-hand side is equal to the right-hand side. So now we are in position to prove the Weyl character formula. So we need to prove that our element D from the previous slide, so the denominator, when multiplied with the character of L lambda, gives us the alternating sum over all elements in W, so the coefficient is the sign of W, the exponents of W applied to lambda plus rho. We know that the character of a simple finite dimensional module is W invariant. So now take a simple root alpha, then applying S alpha to the left-hand side, we get minus the left-hand side. So the character is invariant, and D from the previous slide gives us the minus sign. Recall that we already established that the classes of the Verma modules form a basis in the Grothendieck group of O. So hence, the character of the module L lambda is a linear combination of characters of Verma module. So this should be delta W dot lambda. The character of the Verma module delta W dot lambda is, as we have already seen, so we take the highest weight, the exponent of the highest weight, the exponent of W dot lambda, and we divide it by the element D times the exponent of minus rho. So this comes from the previous slide. And now we can rewrite it as the exponent of W applied to lambda plus rho divided by D. Since for all simple roots alpha, as alpha of the right-hand side is equal to minus right-hand side, it follows that, so we already established this property for the left-hand side, so it follows that the left-hand side and the right-hand side are equal up to some scalar. So we need to compare that some coefficient on both sides is the same. And we can compare the multiplicities of the weight lambda on both sides, and we see that they both are equal to 1. So this completes the proof of the Weyl character formula. So let's consider the SL2 example. So if we take G to be equal to the algebra SL2, then we have the Verma modules over this algebra, delta lambda, where lambda is a weight. And we recall that we have only one positive root, alpha, and that the element rho is 1/2 of alpha. So we know that the Verma module delta lambda has a basis consisting of the elements f to the power I v lambda, where v lambda is the canonical generator of the Verma module and I is a non-negative integer. So therefore, the character of the Verma module is equal to e to the power lambda plus e to the power lambda minus alpha plus and so on. So if we take out e to the power lambda, we will get exactly the exponent of lambda divided by 1 minus the exponent of minus alpha. And if the evaluation of lambda at the Cartan element h is a non-negative integer, then the character of the simple weight module L lambda is equal to the exponent of lambda plus the exponent of lambda minus alpha plus and so on plus the exponent of minus lambda, and this is equal to the exponent of lambda minus the exponent of minus lambda minus alpha divided by 1 minus the exponent of minus alpha. And now if we multiply both the numerator and the denominator with the exponent of rho, we get this symmetric expression, the exponent of lambda plus 1/2 alpha minus the exponent of minus lambda minus 1/2 alpha divided by the exponent of 1/2 alpha minus the exponent of minus 1/2 alpha. Let's make some remarks about characters of other simple highest weight modules. As we have already seen, characters of Verma modules are very easy, and we know that classes of Verma modules form a basis in the Grothendieck group. So to determine the characters of simple highest weight modules, we need to determine the composition multiplicities of simple highest weight modules in Verma modules. This is a hard problem, and the complete answer to this problem is given in terms of Kazhdan-Lusztig combinatorics. This will be treated later in the course. So let's finish with a number of questions for PhD students. So question number 1, determine with all details the characters of simple highest weight modules in the regular block of category O for SL3. Question number 2, let P and Q be two projective or two injective modules in category O. Prove that these two modules are isomorphic if and only if their images in the Grothendieck group of O are the same. Question number 3. Prove that for any weight lambda, the class of the Verma module in the Grothendieck group of O coincides with the class of the corresponding dual Verma module in the Grothendieck group of O. Question number 4. Compute the character of the adjoint representation of G using the Weyl character formula and compare it with all details to the obvious answer for the adjoint representation. We know that for the adjoint representation, the weight spaces are the roots and 0, and all non-zero weight spaces are one-dimensional, and the zero weight space is the rank of the Lie algebra, the dimension of the Cartan subalgebra. And the final question 5, prove that for an integral dominant and regular weight lambda and any weight mu, the weight of the character of L lambda at the point mu is given by the following formula. So it's the sum over all elements in the Weyl group, the sign of this element, times the value of Costant's partition function at the element W applied to lambda plus rho minus mu plus rho. Here, the constant partition function is a function which gives dimension of weight spaces for the universal enveloping algebra of n plus or n minus. So it's the number of ways to decompose a weight into a linear combination of positive roots with non-negative integer coefficients. Thank you, see you next time.